we will come to the topic, subgrid scale physics parameterization. I hope we still have time. Let me maybe talk 5 more minutes. First of all, why do we need physics parameterization? We have to consider what length scales are resolved and what are subgrid scale. For example, for the part of the mesh that has resolution closer than 10 km. This range of resolution is usually called the visual scale. Then, actually, a number of important physical processes are not resolved by the grid. That may include what we will go over later, cumulus parameterization, and also gravity wave thread. Then, the cell is large. If you only carry out the dynamical core, these physical processes was not simulated. But what actually happens in the real world is that these physical processes will affect the variables on that large grid cells. So we have to use a way to account for such inaccuracy. So people will need to implement physics parameterization scheme to compensate what was missing. And then if for the part of the mesh that use a final resolution, then many physical processes are resolved. And for this fine resolution, actually, if you turn on this parameterization, that would be incorrect. So you have to turn off that those invaded parameterizations. So there are gray zones between these scales. Usually, we say that if we can resolve cloud, this is cloud resolving scale or convection permitting length scale, which is usually finer than 4 km, then we turn it off. So in between these two length scales, there are gray zone of which is embarrassing. If you turn it on, then it is wrong. If you turn it off, it is also wrong. So people have to develop scale-aware parameterization schemes. So these are quite new, and development has been done in recent years. And frontier research is still underway. So for some parameterization scheme, you can choose. Some are scale-aware, and some are actually not so scale-aware. So you have to read documentation and do your experiments on what will come wrong if you just choose it and run it. And I think I cannot go into more details of each parameterization. And also I plan only to introduce, take 1 or 2 examples to introduce to you. And for the rest of the different physical processes that may have a physics parameterization scheme, you may just do it in a black box way, just try and error, read documentation, heard about what your friends' experience is, and then use some safe choice. So I shall defer that to lecture 4. And in lecture 4 and 5, I shall also go over some more techniques in analyzing outcoming simulation results. So the next thing to introduce is from Stu's book. The book lists out physical processes that should be handled by physics parameterizations in numerical weather prediction. So I need to introduce these to you. The first one is cloud coverage. If the cell, say, take the picture. If the cell is large and the horizontal grid spacing is very often longer than typical size of clouds, then we should consider putting cloud coverage as a percentage of area that's covered, that cloud is present and cover the cell, and let it be handled by some parameterization scheme. So we call it a subgrid scale cloud. And then the coverage should be related to relative humidity. And so people will devise some formulation to estimate cloud coverage. And then this number will affect radiation budget because in the radiation scheme, it have to calculate whether the sunlight is reflected by clouds and then not reaching the land surface and etc. So this is important, and this should be handled in the numerical weather prediction model. The second one is precipitation and cloud microphysics. I will talk about this in much more details in the later slide. So I introduce other things first, and then deep convection or convection scheme also handled handled in detail. I should introduce just in a few moments. And then radiation, it need to calculate the angle sunlight shine on the Earth according to Earth's orbit and the season and the day and time. And this radiation scheme need to handle absorption, scattering, refraction from cloud, aerosol, and the surface. And then how it handle it need to divide infrared radiation spectrum, different wavelengths, okay, and handle different wavelengths separately. And then you usually see a long wave radiation scheme and short wave radiation scheme, and it will affect heating of air and the Earth's surface. Usually the choice is quite standard. There is one scheme that many people use. So you use that choice, and then so we don't go into detail of it. Turbulence near the surface, subgrid turbulence intensity need to be estimated. Usually they are affected by resolved winds and buoyancy. And then near the land surface, it has to handle heat floods, moisture floods, and momentum floods. And usually the methods to handle that is the following, but I should not go into details because the formulations are quite difficult. And there are two choices, but I will introduce how to follow people's choice to choose it. And then the boundary layer parameterization scheme is the lowest altitudes near the Earth's surface, and the vertical profiles of temperature, humidity, and wind need to be calculated by some formulation as resolved stage of turbulence and forecast of the depth of the boundary layer. And we will come. This is also a complicated topic, but maybe tomorrow I can share how we can learn about it. And then the surface model includes a land surface model, or actually ocean surface. It need also be handled, and also for areas near the North Pole and South Pole, they are usually covered by snows and ice. So the albedo, the fraction of radiation energy reflected out, are quite different for land, ocean, and near the poles. So they are handled by the surface scheme. And then the roughness of the surface, especially for land surfaces of different land use. And then, and also vegetation greenness, it affects heat flux and moisture flux. So they are handled by the surface scheme. And for our simulation, usually we care the land surface scheme used, but the NOAA scheme is a choice that many people use. And also there is a more advanced and more complicated survey scheme called NOAA MP, but you need to be more you need to care more about the details when you use more complicated schemes. So in CPAS, we just choose the NOAA scheme. And then subsurface heat and water, that is related to the part that model soil moisture and soil temperature. So as I introduced previously, you should use model with more than one layer for soil, so that they can produce a more accurate simulation. And the last one is called mountain wave drag. And also in Lecture 5, if we have time, I shall also share my experience on learning more about it. It's about when the cell is large and there is variation of terrain height within the cell, we have to be careful to represent it with some static data, subgrid scale orography statistics. And then this mountain wave drag parameterization scheme shall take that as input and then do some calculation according to some formulation on how gravity waves may be generated and then affect the atmosphere above. So these are a number of important processes that will be or should be taken care of in a numerical weather prediction model, but there is a variety of model. So for two models, we should be familiar to the Wolf model, which is the most popular models nowadays, which we can look into how many choices are already present or supported in this open source model. So you should get used to it. If you go into their page, which is open here, you will see the page the Wolf organization provide to its users, and it introduces Wolf model physics options and references. This page is very long. Okay. And then the ways that these physical processes have to take care how they are organized into the Wolf model may be different from model to model. So for classification, you will see that Wolf classify this model into in this way. And some name may be different, but they carry very similar meaning. For example, cumulus physics, you will see some people call it deep convection parameterization or convection scheme. And maybe you will see cumulus parameterization scheme. Basically, they are the same thing or very similar things. So there are many choices. And when you need to drill into detail, you just visit the page and then click the section, and then you will find how to specify to use that scheme involved. This is by specifying the number. In MPass, this is in another way. And then you will see the originating paper, and then you can check if you are interested in the YSU scheme. And then if you are a researcher, then you check the paper, and then you will see that this is this kind of thing. So for beginners, it is quite difficult to learn. So another way you get information of what they are is another page. This page, the user guide, and it is hosted as a web page. So this is the page. The link will go to, this is also long. And then you look into when you are running WRF. So many topics, and then physics and dynamics option, probably this one, you go into it. And then for each scheme, say microphysics, we will talk about WSM, this one, WRF single moments, WSM 6 class. And then you will have a very brief description of the model. Usually, when we try to understand some complicated thing, we try to look for summary information first. So this page may help, because this page is already quite long. And if you get very summarized information from this page, then this is a starting point. And then we are not really learning WRF, so we learn something like the next generation of WRF, that is using unstructured grid and available as the open source MPass model. So you can check its user guide, just Google search it or visit its website, and then the user guide is long, and you have to go to the correct chapter and look up the correct sections and the correct table or figure. So I've done it for you. It is table 6.3. So out of the many choices available in WRF, when the MPass software is developed, it takes only maybe some popular ones out of the long list of available choices. So these are the shortlisted or implemented or ported parameterization scheme available in MPass. And then CPAS is a modified version of MPass, and basically it takes all the schemes available from MPass. So we will, and when you use it, you just mention the name, not a number, and then this will ease user from the lookup task. You just memorize how to spell the name, and if you use it from a terminal, and then you have to edit the configuration files and do the hands-on work. But for CPAS, we try to provide a user-friendly cloud operation, cloud service interface for users. So you have already seen that in the real simulation job ordering page. You may see model option, which by default, it doesn't open, it is in closed state. And if you click it, you can open it. And then the first thing you see is that you can choose something called physics suites. And you have 3 choices, and none is for some special idealized tests. So for real simulation, you have 2, usually you consider 1 choice out of these 2. One is called mesoscale reference. The other is called convection permitting. So we can come back to this introduction. Usually for resolution coarser than 10 km, this is just an indicative number, and this is just mentioning the order of magnitude. not very exact. We call it visual scale. And for resolution finer than 4 km or 3 km, the grid spacing is already of the same length scale of cloud. So it is already having the capability of resolving cloud or permitting convection to appear in your simulation. So very often we call this resolution or resolution finer than this to be convection resolving or convection permitting. So this is this range of resolution. So to ease user to choose parameterization scheme, CPAS itself already defined the concept of suites. So it have a collection of some default choice of scheme, which is good for this length scale for you. So it has chosen convection to use this scheme, microphysics to use this scheme, so on and so forth. And I will go into detail for the first two one. And then for radiation, you see both choose the same one. So you don't need to choose, and you spend time to go into detail. And if you like this as a research topic, so for the others, also the same. Okay.